Welcome, everyone. Today, we're going to dive into a fascinating phenomenon, when perfect agents hallucinate together. Instead of looking at multi-agent hallucinations as just another AI glitch, we are going to reframe this issue as a classic distributed systems failure, based on the insightful research by Carson Rodriguez-Saleb. Let's start by looking at what we call the illusion of agreement. Often, we mistakenly think the AI model itself is failing, but the failure is actually in the interface. When you look at individual models in isolation, they are surprisingly accurate and coherent. However, as we deploy these large language models into multi-agent setups, a novel failure mode emerges. Agents behave like two highly intelligent people who are reasoning flawlessly, but based on completely different sets of information. So, while each agent is correct in isolation, together they end up collaborating to produce factual contradictions and hallucinations. This brings us to a core concept, context drift. This is the progressive divergence of what different agents know while they are working together asynchronously. This drift happens across three primary dimensions. First is spatial drift, where agents form divergent beliefs about their shared environment, like having the wrong location data. Second is temporal drift, which means they are operating on different timestamps. One agent's current state might just be another agent's stale cache. Finally, there's task drift, which involves conflicting assumptions about their accumulated history, such as what decisions have already been made or ruled out. Now, the intuitive fix for context drift might seem obvious. Just force the agents to communicate their state to each other constantly. But this leads us straight into the contamination paradox. Indiscriminate communication actually amplifies errors instead of resolving them. Looking at our data in the travel domain, adopting a naive full broadcast synchronization method caused a massive 34% increase in hallucinations compared to a baseline where agents didn't synchronize at all. Let's break down the anatomy of a cascade to understand why this happens. Imagine agent A, a booking agent, gets a fact wrong, say, it selects the wrong airport. If it indiscriminately broadcasts this state over the network, it propagates that error to all its peers, like the planner and advisor agents. The result? The system achieves consensus because everyone agrees, meaning divergence is low. But they are agreeing on a hallucinated reality, which degrades the overall task coherence scores by a staggering 33%. To solve this, we first need a way to measure misalignment, which we do using the CDS metric. Instead of sharing massive, raw text contexts, agents generate compressed semantic embeddings of their internal state. These are 384-dimensional vectors. We then calculate the cosine distance between these states in real time. If the score exceeds a specific threshold, we use tau equals 0.25, it acts as a trigger, signaling that continuing to reason together will likely produce inconsistencies. This logic forms the backbone of SSVP, or threshold-gated synchronization. The core idea of the shared state verification protocol is that it only intervenes when divergence absolutely requires it. During a local reasoning step, an agent generates a lightweight context summary with almost zero overhead. If the CDS is under 0.25, silence is golden, the agents just resume joint reasoning. But if the CDS spikes above 0.25, it triggers a context merge. The agents pause, exchange their full contexts, and explicitly adjudicate conflicting authoritative states using timestamps to prevent silent, accidental overwrites. Let's look at the results in our synchronization showdown. When we compare our SSVP method against having no sync or full broadcast, the winner is clear. SSVP achieves the lowest hallucination rate at 46.3%, while simultaneously reducing API calls by 58% compared to the heavy full broadcast method. Most importantly, it gives us explicit, early detection of conflicts. The conclusion here is simple: smarter communication beats more communication. We can visualize this danger clearly in what we call the contamination trap. If you look at this graph, the full broadcast method maintains the lowest divergence, but it traps the agents in a shared error, yielding the highest hallucination rate at nearly 66%. The key insight here is that merely forcing agreement is dangerous. SSVP accepts a little bit of transient divergence and only triggers synchronization to reset the system before those errors are permanently committed. It's also crucial to ask, when is this contamination risk highest? We found a stark contrast between domains. In the travel domain, where beliefs cascade, meaning a wrong destination leads to a wrong airport, which leads to wrong weather, the contamination risk is exceptionally high, and full broadcasting destroys accuracy. However, in domains like software development, where beliefs are often orthogonal, like dev platforms versus QA requirements, the risk remains low. Regardless of the environment, SSVP serves as the safest default for both. Ultimately, we need a paradigm shift in how we view multi-agent hallucinations. The outdated approach tries to fix the model using techniques like RLHF or endless prompting. The modern paradigm focuses on fixing the interface. We must stop treating cross-agent misalignment as just a language modeling deficit. In reality, multi-agent hallucination is a Byzantine fault. Just as distributed databases rely on eventual consistency protocols, multi-agent AI urgently requires context synchronization and tools like Lamport clocks as first-class primitives. To wrap up, here is a simple heuristic for designing future agent architectures. The right question to ask isn't how much should agents communicate, but rather what should they communicate, and when? The golden rule takeaway is that silence is golden. By using selective, threshold-gated synchronization, we can avoid cascading contamination, drastically cut API costs, and resolve contradictions long before they compromise the final output. SSVP isn't just a fix, it is the necessary evolution for distributed AI. Thank you.